Good morning, good afternoon, or good evening. All right, so our topic Monday, Tuesday of this week is air masses in fronts, and today's an absolutely perfect day for that because we have a developing storm system that's going to reach, the point of occlusion. So I'll talk about a little bit of why inclusion is pretty darn awesome and what it means for us. So current surface map, we have, and pardon me, I'm like gonna move through a bunch of different apps right now, and I'm looking at two different screens. But low pressure systems or mid latitude cyclones are designated by red L's because they they indicate that there's a lot of upward motion of warm, humid air. So we designate that with L's. And you can have multiple areas of low pressure, but the main area of low pressure is right there, pretty much over central Pennsylvania. And what makes this system dynamic and unique is you have a number of warm fronts, which we designate with red semicircles. And then cold fronts, because they're a little more fierce and the air is moving quicker, and it's the boundary between cold air and warm air, we use blue. There's actually two cold fronts associated with this system, there and there. So key component as we talk about air masses and fronts is fronts separate air masses. So air masses have two parts. They have a temperature part and they have a humidity part. And with humidity, you're basically one of two types. You're either dry or you're humid. Temperature, you can be hot, you could be warm, you could be cool, you could be mild, you could be cold, you could be Arctic. And so you combine the temperature piece with the humidity piece. So if you take Arctic and cold and warm, that's three temperature variations. With humidity, you're either dry or humid, that's two variations. So you combine those, there's basically five primary types of air masses, because you can't really have an Arctic and a humid. You can have an Arctic and a dry. So it's not six, it's five. Five main air masses, but we're usually only concerned in basic earth science with, is the air mass dry or humid, or is it cold or warm? So the piece here that I wanted to connect with a real world application, and we'll get into some more detail too, is there's an air mass here that's cold and dry. Yes, it's sloppy. It's a double cold front because here it's not really as humid and warm as it is here, but it's still different. So that's why they have the double cold front. All right, this is really difficult to mouse it out, but whatevs. Warm and humid. Here, it's a little cooler, not as humid, cold and dry back here. So what the storm system is going to do, the cold front's actually going to catch up to the warm front, max out the storm's energy, and I'll show you how that happens. And then the storm's just going to dissipate over the course of a few days. That's going to happen up here. So this storm is going to traverse to the north-northwest. All the snow always occurs on this backside because you have to have, in this counterclockwise flow, because the air is going in this direction, you have to combine that tropical, rich, humid air with the cold, dry polar air. So you get this snow shield right on the backside. And we are not going to experience that because the storm's to our west. We get snow when the storms are to our east, slightly. What we're actually in the severe weather sector in between the cold front and the warm front because the air is spinning so fast. Let me show you that. Stationary fronts, by the way, are when the cold front and the warm front can't really decide which one's going to win. So they stay in the same spot. So they're stationary. That would be triangles on one side, semicircles on the other. It's like a combination of the blue and the red. Where occluded fronts, because the cold front catches up with the warm front, it becomes purple. Blue, red, purple. All right, so I'm going to shut that one off and take you to this awesome site. All right, so this is current. We are there. I mean, look how windy it is out here in the ocean, over the ocean waters. I mean, 40, 52, that's sustained. That's not gusts. That's surface wind. Okay, so I'm just going to plop this down here. We're at about 17 miles an hour at the moment. And low pressure, as we've talked about. Bam. There it is. You can see it because of the spin. Look at all that polar air coming down from Canada. You got this tropical air coming up from the Caribbean, wrapping into the storm here. You got your wraparound there, and there's your counterclockwise flow. Cold front, really easy to see. You want your boundary between wind direction or temperature and humidity. So we're going to just put this right here. Keep it simple, even though there's like two. And these have your triangles. And then, oh man, I lost it. All right, I'm just going to use the same color. Low pressure, cold front, warm front. Let's give this low a little respect. It's a good one. There we go. See how much vorticity there is in here? I mean, that's a lot of spin. You have air going this way. You have air coming in really fast this way. You have air coming in this way. And then you have this air digging under. It's not a cross section, but it's digging under the warm air and it's lifting it. This site will show you an animation. What's happening? We're right here. There's our storm system. Animate. Actually, I'll manually do it. See how it spins, spinning, spinning. You got snow on the backside. And right here, that's when it maxes out, it occludes. And it basically rains and snows itself out. So let me back up. So it moves north and it gets caught. The jet stream kind of like slingshots it backwards and then it gets cut off. So right here turns into a snowstorm for the Great Lakes, spins, 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 and then our cold air dives in and dominates pretty much the rest of the week. Cooler, drier weather with maybe a snow shower. That could occur. Don't know yet. There's our current radar. I'll loop this. You can see the storms coming in. Actually, you know what? Let me bounce out. Bounce out of this. There we go. I like the topo off. And then we'll loop this thing. Yeah, there it is. So we got our line coming in. There we are. There's a thunderstorm, little mini squall line meso vorticity right there. Another squall line is going to come in later. There, it's back here in Washington. That's firing up. So what did they do? I'll show you. So we got a tornado watch. So right. I have to keep the mouse on there. All right, so right there. So we're on the northwestern fringe of that tornado watch, and I'll show you why. Here's a current surface map. These are like more professional sites. There's your low pressure. These are wind barbs. You got the wind wrapping around this way. Okay, but just because you have that scenario does not mean that you're going to be issued a tornado watch. It just means it's low pressure system's doing what it should, but it's pretty strong. A 994 getting stronger than a 994, is a danger sign. So I'm going to look for helicity. Let's just go to your basic surface storm relative helicity. Let's just keep it simple. There we go. This is showing the potential for rotation, so to speak. So helicopters, spin, helicopter, helicity, spin. If you look outside, over the next hour or two, you'll just look up at the sky. You'll see the clouds are moving incredibly fast, and that they have somewhat of a turn motion to them at different levels of the atmosphere. So air might be moving in a slightly direction at 5,000 feet versus 10,000 feet versus 15,000 feet. Here, I'll give you a little preview. Go back here. Close this out. I will load up the 500 millibar map, which is at about 18,000 feet, and there you have this puppy. I mean, look at how fast this is moving. Like, this air is jetting. There we are. At 18,000 feet, there's your jet stream. It goes this direction, and then it just decides, let me go the opposite direction. Boom. That's going to create a lot of spin. Here, the air is hardly moving at 18,000 feet. Like, if you lifted a helium balloon, this is how it would travel. It would just go bloop. And if it got stuck in this eddy, so to speak, it would just sit there in the atmosphere. It's almost like, this is like the eye of a hurricane, because this is what the atmosphere does in a strong storm situation. Except this is like the eye of a hurricane at 18,000 feet. So back here, before I shut things down, this is where the air has the potential to rotate. We're not talking like Kansas, Oklahoma, Alabama, North Dakota risk for tornadoes. It just means that the air has spin, and you can produce a tornado or a rotating thunderstorm or straight line winds. So in this section, highest risk down here in the Delmarva, those are your higher numbers. We're on that northwestern fringe. Basic weather forecasting, you pull up this map, you work for the Storm Prediction Center in Norman, Oklahoma, you're going to issue a tornado watch where your strong helicity values are, especially when you have an intensifying low pressure system to the west here. And I know we haven't gotten to this, but when your trough is this deep and it's starting to do a negative tilt, a negative tilt is when this jet stream turns, but it's forecasted to start going like this. You combine that speed with helicity, you're going to issue a tornado watch, just to give people a heads up that you could have severe thunderstorms with the risk of one dropping a tornado. But around here, tornadoes are usually weak, whereas our main risk with when we're issued a tornado watch is you're looking for squall lines that can create little vorticities in the thunderstorm itself, and also create straight line winds, which is when the wind comes down so strong, it hits the ground and it sort of spreads out, and it can cause a lot more damage than just a little tornado. All right, so that's fronts, air masses, storms. Remember, fronts, you have cold, warm, stationary, occluded. Air masses are what create fronts. The boundary between any air mass creates some kind of front, one of those four fronts. All right, have a wonderful day.